Having looked at the muscles themselves and most recently looked at the nervous system and its role in triggering muscular contraction, we are today going to be looking at the mechanical events within the muscle fiber itself that lead to the generation of force and ultimately then help produce movement. Um, the system by which this happens is called the sliding filament theory of muscular contraction. This was first hypothesized by a man named Huxley in the late 60s. Two of the original papers on this theory are available on Schoology should you wish to read them. Um, Not essential reading for the course, but some interesting background stuff. We will briefly revisit this overall structure of a muscle. So, a fairly generic or standard skeletal muscle here, tendon at one end, which will be anchoring this muscle to the bone for its insertion point. Um, we've got that tapered at the end of the muscle belly, and within that muscle belly, we see all the fibers and the arrangements thereof. So your muscle is made of hundreds and thousands of muscle fibers, each of which run the length or the entire length of the muscle. Okay, those fibers are grouped together into bundles called fascicles, and around these bundles, and then even around individual fibers, we have various layers of connective tissue. Okay, so surrounding the whole muscle, we have the epimysium, and surrounding each fascicle, we have the perimysium, and then surrounding the individual fibers within the fascicles is the endomysium. So these layers of connective tissue play important roles, and they help to anchor all these fibers to one another, um, anchor the fascicles to each other, and then connect all those fascicles together. And the connective tissues run through the whole muscle. They all join together. They eventually all join together with the tendon. And what they ensure is that when the tension or force is created within muscle fibers, it is passed on through the whole muscle. So we will get a contraction of the entire muscle, even if only a small number of fibers are actually actively contracting themselves. Now, we're going to be going deeper into those fibers today. So as you can see, extending out of that fascicle, we've got a single muscle fiber. We can see then the cross section of that muscle fiber. We have a number of myofibrils within there, all surrounded by sarcoplasm. Sarcoplasm is a sort of gel-like substance, and it's within the sarcoplasm where we have stores of myoglobin, glucose, creatine phosphate, and other such substances. Okay, the myofibrils within there, again, run the entire length of the muscle fiber itself. They are, or I should say, you have tens, possibly up to 100 myofibrils within a single muscle fiber. And then if we delve deeper into that myofibril, we have a number of protein filaments. Okay? And it's at that level where the protein filaments, we can see those tiny little strands sticking out of the myofibril on the diagram. It's at that level where the actual mechanics of muscle contraction occur. So those protein filaments do not run the entire length of the myofibril. They are very, very short, and they are housed together in repeating structures called the sarcomeres. So from this point onwards, we'll be looking at sarcomeres, and it's within that tiny functional unit where a contraction is produced. If you remember when we first introduced skeletal muscle, we said it was sometimes referred to as striated muscle. So it is the arrangement of the filaments within the myofibril that give it this striated appearance. So we have thick bands and light bands to give us this kind of red and white striped appearance that runs through muscle fibers. Now, this is due to the arrangement of the sarcomeres, um, end on end along the entire length of the myofibril. So somewhat like train carriages, we have this small arrangement attached back to back. So on the diagram, you see the myofibril extending out. We've then got a close-up of that to see the arrangement of various protein filaments in there. Identified on there, so we're looking at sort of the middle picture here, the thin filament, which is the actin filament, and the thick filament, which is the myosin filament. We have a few other things identified on those. We've got the Z disc, which is a sort of dense structure which attaches one sarcomere to the next. And then we've got some descriptive areas, H zone, M line, A band, I band. So the A band, first of all, is that's kind of like the dark stripe that runs through the muscle fiber. The A band is just the width of the thick filament, and that does not change at all during contraction. The thin filaments overlap with that myosin filament. So if we look at the very bottom diagram, which is just a nice simple sort of representation of how a sarcomere is structured. And remember, this would be repeated for the entire length of that myofibril. So we can see that thick filament, dark red, the myosin, and that's what gives us the A band. Overlapping with that, we have the thin filaments, actin filaments, blue, overlapping from each side. A gap in the middle is the H zone. So the H zone is the gap between the thin filaments coming from each side. The H zone, when the muscle contracts and shortens, the H zone will get smaller and possibly even completely disappear. As a muscle is stretched out, the H zone will get bigger. Another filament to mention is, you can see it in yellow on the diagram at the bottom there. This is called the titin filaments. These are elastic filaments. These attach the myosin to the Z discs at each side, and so they ensure that the length of the sarcomere stays as it is. And it's these elastic filaments that help a muscle return to its resting length when force is no longer being produced. The M line runs right through the center of the sarcomere, so that is non-changing, but it is a protein filament of its own, myomesin. Okay, what that's there to do is just sort of stabilize the layout of the fibers through it, and ensures the sort of the structure of the sarcomere, as it were, so anchors those myosin filaments right in the center. The one other descriptive on here is the I band, and that is the distance between thick filaments within neighboring sarcomeres. Okay, we don't need to get too heavy into the different bands and the different zones. The most important thing for us moving forward is the layout of the thin filaments with the overlapping of the myosin filament in the middle. And it's going to be the interaction of the myosin and the actin which is going to be the most crucial aspect for us in terms of sliding filament theory. So we'll take a closer look at the thick filament. This is one of the two key contractile proteins that form our myofibril. And so there are approximately 300 molecules of myosin which are bonded together to form this single thick filament. So we can see on the diagram on the right hand side there, part A at the top is a single myosin molecule. Part B at the bottom shows how we have a large number of these myosin molecules all bonded together to create the thick filament. So the myosin molecule is shaped somewhat like two golf clubs that are twisted together. You've got the myosin tail, which is the golf club handle, as it were. that points towards the M line in the middle of the sarcopene here. And the tails of all these neighbouring myosin molecules lie parallel to one another and form the thick filament. You've then got the two projections coming off each myosin molecule, somewhat like the golf club heads. That's the myosin head, and these are what are going to form cross bridges, which are going to be crucial in muscular contraction that we have shortly. The heads project outward from the shaft in a spiraling fashion, so they go all the way around the outside, as if sort of wrapped around the thick filament in the middle. The thin filaments extend outwards from the Z discs at the ends of the sarcomere where they are anchored. And the thin filament's actually made up of a few different proteins. The major aspect is the actin protein, and this is another one of our contractile proteins. Individual actin molecules join together to form the actin filament in sort of a twisted helix, and this is the yellow spheres that you see on the diagram below, or the orange spheres, I should say. On each actin molecule, there is what's called an active site. You can just sort of make that out in the diagram. The darker orange spots on the orange sphere, and they're covered by this other regulatory protein that we have. There are two regulatory proteins, tropomyosin, troponin. Tropomyosin is a sort of a protein filament that wraps around the actin filament, and you can see it almost like a rope on the diagram. Troponin attaches to the tropomyosin. Now, what the tropomyosin is actually doing at this point is covering up the active site. The active site, also known as a myosin binding site, is where our myosin thick filament heads will attach to actin during the process of contraction. As is here on the diagram, this is a resting muscle. Tropomyosin is in a position where it covers those active sites, and the troponin is holding it in place. Okay, so in order to start a contraction, there's going to have to be some other steps come into play. In order for muscle contraction to then stimulate the tension we need to cause movement, we're now going to have a step-by-step process. Okay? The first step is stimulation of the muscle fiber. From last week's sort of sessions, we know this comes from the central nervous system. The processing of information occurs there, a motor response is chosen, and an action potential is generated. That action potential propagates along the motor neuron, and it reaches the axonal terminals, which form a neuromuscular junction or synapse with the muscle. The action potential is carried across that synapse via the release of neurotransmitter. This causes depolarization then of the muscle fiber itself. Okay. If you remember, depolarization is a change in local charge from approximately minus 70 millivolts to become more positive. Within the muscle, once depolarization occurs, we then get the release of calcium into the muscle fiber itself. And this is going to be the first key step that is going to trigger contraction. Such an important step that calcium can be treated as a key regulator of muscle contraction. So we've got an end-on view across our filaments here. Again, we can see the thick myosin filaments, purple with the golf club myosin heads sticking out. We've got the actin in the middle in a spherical shape this time, red with yellow active sites, and we can see troponin, tropomyosin blocking those active sites. Now, when the muscle tissue is depolarized due to an action potential, we get this release of calcium. within the muscle, I mentioned previously, we've got sarcoplasm. Sarcoplasm being a gel-like substance that surrounds all the myofibrils. Within there, we have another structure called the sarcoplasmic reticulum. These are fluid-filled sacs that sort of attach to the wall of the myofibrils. Once the muscle fibre is depolarized, the sort of gates within open and calcium can flood into the muscles. This is, as I said before, this is key really in terms of controlling the action. Calcium binds to troponin, and when it binds to troponin, it triggers it to change shape. This in turn moves tropomyosin. Remember, tropomyosin being one of the regulatory proteins that at rest covers the active sites on the actin. So now it's changing shape. It moves away from those active sites and frees them up. And this is the start then of the contraction cycle. So we can see it, we've got three diagrams across the bottom of the screen, A, B and C. A being the resting state, tropomyosin and troponin blocking the active site, so we have no attachment between the myosin and the actin. B, due to nervous impulse, calcium is being released. Calcium attaches to the troponin. This causes the troponin tropomyosin to move and reveals the active site upon the actin, and this then leads to diagram C, cross bridge formation. The heads of the myosin attach to the active sites on the actin, and this attachment is what we call the cross bridge. Important to note, this is a natural affinity. Whenever these active sites are exposed, myosin will attach. There's nothing else needs to happen to cause this attachment to occur. Right? As long as calcium is present in the muscle, tropomyosin will reveal that active site and myosin will attach. That is its go-to position. That's where it wants to be. Okay? And so now we've generated some degree of tension. Right? The two contractile proteins are attached to one another, so we couldn't be pulled apart right now. So to build our step-by-step process, again, starting point, stimulation of the muscle fibre due to the arrival of an action potential. Next step is the release of calcium from the sarcoplasmic reticulum. Obviously, we've just outlined a few sub-steps within there involving the release, the movement of troponin and tropomyosin. The next step would be the actual sliding of the thin filaments towards the middle of the sarcomere, happening at both sides, thus making the sarcomere shorter. That will happen in each sarcomere along the entire length of a myofibril to cause shortening of that myofibril in total. There are, however, several steps within this shortening that we now need to cover. At a filament level then, we have got a 5-step process by which the sarcomere is shortened. Right? And this is going to be a repeating cycle of processes to allow continual shortening of the muscle in terms of creating a full contraction. So to start with, we'll go over a couple of the steps we saw previously. Diagram on the bottom left is again our resting muscle. Troponin and tropomyosin are blocking the active sites on the actin, so there is no attachment between myosin heads and actin filaments. Step 1 is what we saw previously, the exposure of the active sites due to the release of calcium into the muscle. Calcium bonds to the troponin. This causes the troponin-tropomyosin complex to change shape, and the active sites are therefore revealed. Step 2 is then the formation of our cross bridges. As soon as those active sites are revealed, the myosin head will attach to them. Step 3 is where we start to see some movement. Right? As soon as that myosin head is attached to the actin, it will pivot. Right? This is what's often called the power stroke of contraction. The myosin head pivots towards the center of the sarcomere. All the myosin heads which are attached do this, and this will generate enough of a pulling force to pull the thin filament towards the middle of the sarcomere, and effectively shortening it a very small amount. You can imagine we're in the realm of nanometers here in terms of how much movement we get from one power stroke. Into step 4 now. At the end of the power stroke, the myosin head is still firmly attached to the actin. Remember, that's a natural affinity, so it's not really interested in letting go. If we want further shortening of the sarcomere, which we will, one power stroke won't be enough to cause any sort of real amount of movement. We're going to have to detach those cross bridges to allow them to reattach further down the thin filament. In order to do that, we need a substance called adenosine triphosphate. A lot of you will have heard of that before in previous studies, and potentially already mentioned by us earlier in this module, in that adenosine triphosphate is the only substance the human body uses for mechanical energy. So we have to have, if we're going to have muscles contracting, it is adenosine triphosphate that's responsible for that. The other energy substances in the body, phosphocreatine, carbohydrates, fats, proteins, they are all converted into adenosine triphosphate to then be used for muscular action. And it is this microscopic level where that ATP is actually harnessed to allow muscular movement to occur. So once the power stroke has occurred, a molecule of ATP will bind to the myosin head. The binding of the ATP to the myosin head will cause it to detach. It's probably worth mentioning here, not all myosin heads will detach at the same time. There will always be some still in contact. If they all detached, the natural elasticity of the muscle would cause it to return back to its normal position and lengthen again. So the attachment of ATP to myosin will cause the myosin head to detach. This leads us into step 5. For it to grab on again, we need that head to go back to its original position, okay, to pivot back. And we're not going to get too deep into energy now, because that is a subject for physiology of human performance in semester 2. But like all chemical substances, ATP is made of various different molecules attached together via chemical bonds. It's within chemical bonds where energy is found, and the breaking of bonds that releases energy and allows it to be harnessed for other purposes. So we break ATP up in a reaction called hydrolysis, and this is catalyzed by an enzyme called ATPase. So this hydrolysis breaks ATP into ADP, and the energy that's released during that reaction can be harnessed to sort of re-pivot the myosin head back to its original resting position. Once it's back in its resting position, this then leads us back to step 1 of the process. Now we're back at step 1. As long as we have sufficient amounts of calcium in the muscle, the active sites remain open and the cycle will repeat. Myosin will hold on, it'll pivot to pull the thin filaments even further into the middle of the sarcomere. As long as we have sufficient ATP, that can then release, reset, and go again. So the continued contraction of this muscle and continued shortening is going to be reliant upon nervous system stimulation adequate levels of calcium and adequate levels of ATP in the muscle. So we'll have then a process almost like a tug of war, hand over hand. You grab, pull, release one hand, grab further up, pull again, release the other hand, grab and pull. And this will gradually draw the thin filaments towards the middle of the sarcomere and cause it to become shorter. This is a very, very fast action. So each of the 600 myosin heads in any one thick filament will attach and detach about 5 times per second. As mentioned before, at any given time, some of the myosin heads will always be attached to the actin and generating force, whereas some of the others will be detached and available to reset and bind again further up. This is allow us to gradually draw that thin filament in towards the middle of the sarcomere and thus shortening it. We therefore have completed a number of steps. So if we go over the whole process, remembering each one of these points can then be fleshed out to create further steps. So we get the stimulation of the muscle fiber from the nervous system. That causes calcium ions to be released. This then triggers the sliding filament mechanism that we've just discussed in some detail. That causes the thin filaments to move towards the middle of the sarcomere. Sarcomere shortens. As this is happening at repeated sarcomeres along the entire length of myofibrils, this will cause contraction, shortening of an entire muscle fiber. Tension in the muscle therefore increases. This will pull on a tendon, the tendon pulls on the bone, and we get some form of visible movement at the end of it all. So, a lot to take in there. On the next slide, you're going to see a brief video which will show you some of this stuff in action in an animation form. And I would recommend
Muscle contraction is at the basis of all skeletal movements. Skeletal muscles are composed of muscle fibers which in turn are made of repetitive functional units called sarcomeres. Each sarcomere contains many parallel overlapping thin, actin, and thick myosin filaments. The muscle contracts when these filaments slide past each other, resulting in a shortening of the sarcomere and thus the muscle. This is known as the sliding filament theory. Cross-bridge cycling forms the molecular basis for this sliding movement. Muscle contraction is initiated when muscle fibers are stimulated by a nerve impulse and calcium ions are released. The troponin units on the actin myofilaments are bound by calcium ions. The binding displaces tropomyosin along the myofilaments, which in turn exposes the myosin binding sites. At this stage, the head of each myosin unit is bound to an ADP and a phosphate molecule remaining from the previous muscular contraction. The myosin heads release these phosphates and bind to the actin myofilaments via the newly exposed myosin binding sites. The two myofilaments glide past one another, propelled by a head-first movement of the myosin units, powered by the chemical energy stored in their heads. As the units move, they release the ADP molecules bound to their heads. The gliding motion is halted when ATP molecules bind to the myosin heads, thus severing the bonds between myosin and actin. The ATP molecules are now decomposed into ADP and phosphate, with the energy released by this reaction stored in the myosin heads, ready to be used in the next cycle of movement. The myosin heads resume their starting positions along the actin myofilament and can now begin a new sequence of actin binding. The presence of further calcium ions will trigger a new cycle.
Just to emphasize again, the difference here between a relaxed sarcomere and a contracted sarcomere. We can see the H band being the distance between the two thin filaments of the sarcomere, right in the middle. We've got a visible H band at the top when the muscle is relaxed. At the bottom, we've gone through that process of sliding filament theory. The thin filaments on each side are pulled in to the middle of the sarcomere by the myosin filaments, and the H band decreases. This, as you can see, between those two diagrams, and remember these are going to be only nanometers in size, the actual difference in each individual sarcomere is tiny. However, because we have so many sarcomeres end on end along the full length of a muscle fiber, when these small changes in length are summated for every sarcomere, we'll then get quite a significant change in muscle length overall. And that's all we need to be able to pull on a tendon, which will then be able to create movement at the given joint. Understanding the sliding filament theory and at the level of the sarcomeres also helps us to understand something called the length-tension relationship within muscles. And this shows how much force a muscle can create, or how much force a contraction can create, depending upon the length of those sarcomeres before a contraction begins. We can see sort of the zone in the middle, shaded in green, being the strongest aspects. And when a muscle is stretched out further than that, it is incapable of generating as much force. But also when a muscle is shortened even further than this optimal range, it's also unable to create force. And this is really dictated by the number of cross bridges that can be formed at any given time. At those optimum levels, we have maximal cross bridge formation. When the muscle is shortened too far, or shortened even further, I should say, what we actually get happening is some overlap between the thin filaments, and as such, this is preventing some of those myosin heads from attaching, and as a result, we can't create as much force. If we go the opposite direction, as those muscles begin to be stretched out, the zone of overlap between thin filament and thick filaments is even shorter. Fewer myosin heads can make contact with the thin filament, and consequently the ability to create tension is decreased further. As we stretch even further to the right, approximately 170% of a muscle's resting length, we actually get to the point where there's no overlap between thick and thin filaments. If there's no overlap, no myosin heads can bind to the thin filaments at all, and the muscle cannot contract at all. So tension is zero, and it's going to be completely incapable of creating any force. This is something that can be sort of bear in mind in training. As you put people into various different positions, it is going to affect the ability of muscles to contract. Resting muscles tend to be at sort of the optimum position for firm attachments. So we don't want to overshorten or overstretch if we are then going to expect an individual to contract forcefully.